Hi, today we have a short introduction to algorithms and data structures. What are algorithms and data structures is the first question we have to answer. So nowadays we hear a lot about like algorithms, the YouTube algorithm, the Instagram algorithm, all these kinds of things. But what is an algorithm, first of all, right? What is this word and where does it come from and where does it take us? First of all, this is a word and the concept that comes from math, right? So mathematicians, they use the word algorithm to mean a series of operations that we perform on some number or some value that transform it to produce a result. So let's say that you have a number like 5, and then you perform some kind of operation, like you say you multiply it by 2, and you get 10. This is albeit a very simple algorithm, it is an algorithm. And let's generalize this a little bit more. We could say that our algorithm is to multiply some input, which we're just going to call A, to multiply the input times 2. And then the output will be whatever number is here times 2. So we could also say the output is 2A. And therefore, if we substitute A with 5, we get 10. If our input is, let's say, 20, then the output will be 40. If the input is -2, the output is -4, and so on and so on. So that's really what an algorithm is. It's basically just a set of operations that produce a result. Now, an algorithm doesn't strictly have to have an input and an output, at least in computer science, but it does need to produce something. It needs to do something, right? So like an empty operation, if you would say, okay, you give me a certain value, like a 6, and then nothing happens, right? Like, let's say null. Yeah, like just nothing happens, like an empty program that doesn't do anything. This is not an algorithm. Yeah, so there's a very clear difference between what is an algorithm and what isn't an algorithm. Now, in a broad sense, everything that we program is an algorithm, because every program in itself has a set of instructions, right? Functions and operations and so on, that produce something, right? And most of the time, the program has some kind of input. I mean, it has to. Even if the input is something very trivial, like the time of day or the fact that the program has started, right? Now, what is also not an algorithm is if the program, let's say, always does the same thing, and this thing never changes, like there is no computation. Let's say if my program, all it does is like, let's say that my program is very simple. It has one line of code, right? So I have like my main function, and in my main function, I have something like int a equals 10, and that's my program. This is not an algorithm because it's not actually doing anything. In a more sort of philosophical sense, we could say, yeah, but like the computer is doing something. So from the computer's perspective, there is a change, right? Like the program will run, the CPU is running some instructions to run the program, loads the the instructions and stuff like that. And there needs to be some memory allocated to store the number 10. So something changes for sure. Something happens in the computer. But it's not really an algorithm from the perspective of our program, right? Like from our perspective, we are not really performing any work. We're not transforming data. We're not processing data. We're not getting any input, any output. Yeah, this program doesn't take any information from anywhere and also does not provide any information to anything. So in a more practical sense, this is not an algorithm. Okay, now an algorithm could be we print A, so we can output it to the console, or we represent it somehow. This would maybe be more accepted, more easily accepted as an algorithm. Another thing that, of course, would be an algorithm is that instead of this, we say we read. Right? We read the console or read the user's input, or we read a file, right? Like this read, we can see it a little bit abstractly. Yeah, we read some value from somewhere. It could be from the keyboard, from a file, from the network, from a server, and so on and so forth, right? So this would be more of an algorithm because it is taking the data from one place and displaying it somewhere else. It's still a very simple algorithm, but it is an algorithm nonetheless. So this is the first thing. We have to demystify the word algorithm because algorithms are not inherently something that is very complex or hard or scary, right? It's basically just a program, what we would otherwise call a program or a function or something like that. Now, if it's so simple, why do we have a course called Algorithms and Data Structures? And why do we devote several weeks to this? Well, because there are certain tasks for which specialized algorithms are necessary. This is basically certain mathematical or computational operations or tasks that have already been solved in optimal ways. So we are going into a little bit more of a scientific approach, right? See, this is where we get more of the sort of pure computer science, and we forget a little bit about the sort of creative process, right? Because while we can make our own algorithms, so I could come here and I say, okay, this is the João algorithm, right? Like I invent this thing and whatever, I publish an article, publish a paper about it, and so on. There are many things that we need to study because there are many things that have already been done. And also, even if we want to develop our own algorithms to solve new problems that maybe nobody else has ever faced before, we can still learn a lot simply from studying how other problems are solved and how other algorithms work and why they work, why are they so good or why are they not good. We are also going to take a look at some bad algorithms. Okay, so first thing is there is a coupling here between the word algorithm and the word or the term data structure. And I have mentioned data structures already in the past. And of course, like just from the word, you can see what it means probably, right? It's a way of structuring data, of organizing data. And these two are often coupled together. They go hand in hand. Why? Because usually when we have these sort of big, hard problems that we need an algorithm for, usually we have with it either an accompanying data structure that is created to facilitate the algorithm, or we have an existing data structure and we want to perform some kind of operation on it. So then the algorithm serves to work with the data structure. So either we have some kind of data structure, like let's just go with a very simple example, like we have a table, like an Excel spreadsheet, and now we want an algorithm to do something with it. Yeah, like we want to search certain values, or we want to search how many columns have a total amount of 10 different values. Yeah, so something like this. This would be an algorithm that we perform on a specific data structure. If we had a different data structure, then the algorithm would need to be different. Like if you had the same data, but in an array, right? So instead of having like a table, right? Instead of having basically a grid where, you know, there's sort of like a row, a column and a row, right? You could have the same data. Let's just say we go like A, B, C, D, E, F, etc. We could also just have it in an array, right? Like in a linear array where we just go A, B, C, D, E, F, right? And here the algorithm would need to be different. And probably also the possibilities, the possible things that we do with this data structure are also different. So the way we organize the data necessitates different algorithms. Another thing, another use case, or another reason why these go hand in hand is the opposite. Like I said, sometimes we have a certain algorithm and we need to come up with a data structure for it. Let's say that I have an unorganized set of data. Like, let's say that my user inputs a bunch of data, like some strings, right? So I ask my user to provide like 10 strings, right? So we have like A, B, C, and these are all, you know, not ordered. There's no structure to it. Yeah, the user just types some stuff, some random things in any order, right? Let's say that further down the line, what I want to do is I want to have an algorithm that will find words in these strings. So let's say that these strings could be sentences that have multiple words. Let's say that I want to, in these strings, I want to find words that end in a certain letter or whatever, right? So find X, yeah? I could do the following. I could just go into these strings. I could store them somehow, like let's store them in the simplest possible structure, like an array. So I just store them linearly, like that. And then what I can do is I can have like two for loops, right? I go like for, inside of this for I have another for, and here I go through every word, right? Why do I need two for loops? Because here I iterate over the array, right? So I go to each word, each string. So here I go to the A string, but the A string itself is like multiple words, A1, A2, A3. And then here in this for loop, sorry, my eraser is a little bit too big. Here in this for loop, I go through the words. Right, so then I will Here in this for loop, I will get the A, let's say, right? Here goes the A, and then here goes the A1, A2, etc. And then I can look at each of these, right? So this would be one algorithm, one way of doing it. Another way of doing it is that instead of putting this data in an array like that, I can do this I can do like a pre-pass. I can do this sort of thing previously, and I make an array with all the words individually. So basically, I take each of the A1, A2, A3, and I just put these in their own array. Right, so I can take this out of here. Right. So instead of doing that, I have an array with A1, A2, A3, B1, B2, B3, B4, C1, C2, and so on, right? And then when I want to find something, I don't need the second for loop. I just need one for loop, right? Of course, another thing that I can do is I can, when I process them, when I structure them, I can already do some kind of even more complex organization. So I can already sort the words alphabetically or sort them by length or something like this. So I can already do like one algorithm, right? So I take the raw data, I can use some kind of algorithm to sort them, for instance. So I can sort, I can sort by different parameters, right? Like the length, the alphabetic order, blah, blah, blah. And this then also allows me later, when I want to perform other operations, it allows me to be more efficient, right? Because I could then have an operation where if I know that the data is already sorted, I can design my algorithm or my loop or my function, whatever we want to call it, in a more efficient way, because I can make certain assumptions. Like I can make an assumption that, well, if I'm looking for words that start with A, and I know that my data is sorted alphabetically, as soon as I find a word that starts with B, I can quit because there will be no more because it's sorted alphabetically, right? So I can do this kind of thing, right? So I can say, okay, look for A. So if the first word, the first letter, right? If starts with B, right, or C or whatever, right? Let's just abstract this away, right? If starts with B, then we can just return or whatever, or break, or somehow exit the loop or the algorithm. Yeah. I can only do this if my data structure, in this case, is a sorted array, right? Keep needing more space. So if I know that I have a sorted array, then I know I can make these kinds of assumptions. And this will be the same for all kinds of algorithms, right? Depending on the algorithm I want, I will design a data structure that fits or that allows me to work with this data optimally. Okay, so that's the basis of this. Let's see some examples. I will just show you like a very, very quick example here. And the first one that I will do is going to be the Fibonacci sequence. Actually, before that, I will just do a much simpler sort of example just to demonstrate my point. So I'll make here a function that I will just call a simple, not a sample, but a simple algorithm. And this could be something like this could be something like a 4. And I'm using for loops. We don't need to use for loops, but let's just say that. And then I'm going to console.write I. Okay, so I do this. I have to call it, of course. Did I? Yeah, I have a typo. We're doing it live. And of course, if I do this, we will just print the numbers from 1 to 100, or from 0 to 99 in this case. And this is an algorithm, right? Another algorithm would be if I don't do a for loop, right? Like I could still do like that example that I wrote on the blackboard, right? I'm just gonna comment this out, and I could say like input equals console.read line, and then here I just print the input. Now I write something and then gets printed again, right? So this is a very simple algorithm. This would be a slightly less simple algorithm. Yeah, okay. Another algorithm that is quite common is the Fibonacci sequence, or the Fibonacci series, that you might remember from school. And here we could also we could have a parameter that determines the length, how many Fibonacci numbers we want to print out. So I could do this, and this is very simple. Fibonacci sequence, it's basically something like this. We start at 0. We start with 0 and 1. So these are two known numbers that are given from the start. And then every new number is the sum of the previous two. So then I go 1. And now I take 1 plus 1 equals 2. Now I take 2 plus 1 equals 3. Now 2 plus 3, 5. 3 plus 5, 8. 5 plus 8, 13, and so on and so on, right? So how would we do this? We need to start with two numbers, right? Because I said, okay, we have two initial numbers. So let's just declare them. I'm gonna call them A, and we know that one is 0, and then B is 1. Then I'm going to have a for loop. I'm going to go until the length, right? So that's a parameter that we can receive. So the user can say, okay, give me 10 Fibonacci numbers, or give me 100 Fibonacci numbers. And then we do the loop for that many iterations, right? Pretty simple. Okay, so then we do the following. We add them up, right? Because the next number will also always be the addition of these two, right? And then we need to print it, right? So let's just do a very simple implementation, which will be that we write A plus B, right? And then we need to increase this, right? So we need to do something like this. We need to make sure that now A will be 1, because basically what we can say, okay, A is this one and B is this one. Then we need to make A this and B this, right? So we need to basically remember this value. For this, we need a third variable. So I'm going to use a C variable and do that addition. Now I print my C. And now what I can do is basically just move them around, right? So now the C is the third here, right? So let's just focus on these three numbers. We have A, B, C. All I want to do now is make A point at the second variable, so that's B, and B point at the third variable, that's C, right? So I'm going to do A equals B, B equals C. And that's it. That's pretty much everything. Yeah. Now there will be some weirdness here. If I just run it now, it will not be completely correct because we are not printing the A and the B. So we will only start printing the 1, right? So we start printing here, and then we will go on here, and we will not print these first 2 ones. So I'm just going to run it to make sure that everything is still working. We need to pass here a parameter, let's say 10. And it prints out, like I said, it prints out starting at 1. So it starts on the 3rd number actually, right? And prints then 10 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what we need to do is that we need to make sure that these first 2 are printed. This is very easy. We could make it super complicated. We could go here and try to make it so that these 2 are in here somehow, and like there are some people, they would start at like -1 and blah blah blah, but we really don't need this. All we need is the following. We put a console write line here, we print the A, we print the B, and now here we need to make sure that we do not start at 0, right? So either we start at 2, because we don't want to print 12 numbers, right? Like if I start at 0 and my length is 10, I will print 1, 2 numbers, and then 10. So I will actually print 12 numbers, right? So either I start at 2, or I start at 0 and then I go to length -2, right? This would be the same, exactly the same effect. Although I prefer here to start at 2. And now we start at 0, and then the 1, and then we start the loop, right? So these are these 2, the A and B, and these are then the loop output. 1, 2, 3, 4, 5, 6, 7, 8. And again, I could also do it like this, because from 0 to 10 it's 8, but from 0 to 10 minus 2 it's also 8. Right? So it will give us the same result. We go until 34, right? But I'll just start at 0. Like I said, I prefer it. I think it's a little bit more clear. Okay, so that's the Fibonacci sequence. Very simple. Let's look at some other, one other example. This one will be a tiny bit more complicated, but not much more complicated. But I just want to give you a different input, let's say, right? So what this one will do is it will print the max value of some int array, right? So we will provide an array of numbers, and it will find the max, the highest value in this array, and print it out. So what we can do, again, we will have a for loop. So we're not really going too crazy with any sort of with the algorithm part, yeah. But we're keeping it relatively simple and going more for the variety, right? So here we want to go for array.length. And now what we will do is we need to store what is the highest value that we have found so far. So as we go through the loop, we are going to find some values, right? So let's say that we have numbers 1, 3, 5, 0, 4, something like this, right? Basically, I find the first number and I just store it here in some kind of variable. Then I find the second number, and now I need to compare, is this bigger than that? And it is, so I put it there, right? Then I go to the next one. Is this bigger than that? Yes. I store it. And now I go to the next one. Is it bigger? No, so I don't store it. Is this one bigger than that one? No, so I don't store it. And then at the end, I just print this, because I know that whatever is there is for sure the largest number. That's it. So I can simply declare here a max. And for now, I'll just leave this open here. We will come back to this in a second. And then I will check, okay, if array I is bigger than max, then I say that max equals array I, right? That's it. Then at the end, we print the max. Okay. So this will work only if all the values are bigger than 0 in this case, because this will be the default value of max. So let's say that we have an array of negative numbers, right? Then the max would be 0, even if 0 did not exist in the array. So if I have an array with like -1, -2, -3, it would tell me that the max is 0, right? Because all of these would fail because none of the numbers is bigger than 0. We can test this very quickly. Oh, that's the wrong key. Let's say -1, -2, -3, right? The output is 0. So what do I need to do? I need to ensure that the max is initialized to a value that will always be less than any other value. So there are a few tricks here. So one thing that I can do is I can, of course, can just go for a very small number like that, but I could still probably have an even bigger number, an even lower number, right? Let's go, this one is 6, just so we know. So this ends at 6, this one is 7, this ends at 8. This one ends with 9. And we see, we get the 9, we get the max. So we might think, oh, it's low enough, but it might not be. We cannot tell for sure, unless you know exactly what numbers this will be. Like if these numbers come from some kind of list that you created and it is always fixed, then that's fine. But if these come from like a user or a network or another, person or another computer that you have no control over, then this could be any number, right? So here we have some tricks. We have this fields or these constant variables or these constant fields from the int type. We have the max value and the min value. So I can go here and I can just say this is the min value. No other int will be lower than this. So now I can have these numbers, whatever, and now the max would be this one, the 6. And there it is. Okay. If we would do a min, then we would need to use the max value, right? So a min function would be pretty much the same. Except here I would check, I would set it to the max value. So I would set this one to the highest possible int value. And then here, instead of checking if this number is bigger than the previous, I would check if the number is smaller than the previous, right? And then I can copy this, go for the min, and now the min will be the 8, the 99998, right? That's the lowest number. There it is. Okay, so these are two examples of some slightly more complicated algorithms, right? Like all of these are, of course, very simple. You have definitely written code that is more complicated than this, but I just wanted to show you that these two are algorithms, and algorithms don't need to be complicated. Now, one thing that I want to introduce is, again, a little bit this scientific approach, right? So when we design algorithms, we are, in a way, we are going to put the engineer hat on. So we're going with sort of a more scientific, more engineering lens. And this means that we want to be efficient, and we want to be optimal. What does that mean? That means we don't want to waste resources, we don't want to waste time. We want to find the simplest, fastest, less resource intensive, let's say, solution. And there are some tools that we have to analyze this. First of all, we have some tools that are practical, and we have some tools that are theoretical. So we have here the practical, and we have here the theoretical tools. The practical tool, like the basic one, is going to be profiling. Actually, maybe this is not the basic one. The most basic one would maybe be logging slash timing. So what you could do is you start some kind of timer at the beginning of your algorithm, and then you stop it at the end of the algorithm and you log this. Yeah, so you store this information somehow in a file or print it to the console or whatever. So this can tell you how long your algorithm took, right? And you also have then automated tests. So you could do this automatically. So you could run a bunch of tests. You create some kind of script that runs your program and passes different parameters to it. So you could say, okay, run this algorithm with 3,000 strings, or with 3 million strings, or with 30 billion strings, right? Like, and what's the difference? How does it perform, right, when you increase the load, and so on? Or you run it in different computers and so on, and different machines, different architectures. Run it on the cloud, run it on a phone, blah, 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 blah. Profiling is a slightly more advanced version of this, right? So profiling is basically inspecting the performance while the algorithm is running. Of course, you can also log it. So you can store the information. But profiling usually gives you a little bit more detailed information, like it can tell you how much memory your algorithm is using, or your program, how much memory each specific function or each specific object is consuming, how much garbage is being created, if you remember the garbage and the garbage collector and stuff like this, right? So in C# we can have access to how much garbage the garbage collector is actually collecting, and stuff like that. And then, of course, like the timing. But usually a good profiler will also tell you like how much time was spent on each operation. So it can tell you, hey, this loop here in your program is very slow in comparison to the rest of the program. Or this specific operation, like this line, like you have some instructions, and then it tells you, hey, look, this line here is very slow, or this line here is very slow, for whatever reason. Then it's your job to investigate, and this is also part of being a programmer, is interpreting these errors or interpreting these results, right? That's the practical approach. We test it. We can create automated tests. We can create batch tests to test our algorithms under different conditions and with different sets of data and so on. And then we can look at the results, right? So it's like an experimental, like empirical thing. Then there's the theoretical approach, which is a more mathematical approach. And here we have some fields, let's say. There's algorithm analysis. And this is where you basically, you look at the algorithm and you try to abstract it, you analyze it, like what are the components? What is the input? What is the output? How do you get there? How many operations do you have? What kinds of operations are there? What kinds of data do you produce? Do you produce garbage? Do you not produce garbage? Are there allocations? How many operations per value do you perform? Are you using the CPU in an optimal way, right? This is another thing. Like we can look at it from a computer science perspective and see, okay, this, like on this architecture, this instruction is going to be slower than on the other architecture, and we can actually use a different instruction and blah, 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 right? So this is also a more theoretical thing. Another thing that we look at, and this is what I'm going to introduce now, is the complexity, the algorithm complexity. This is part of algorithm analysis. Now, under complexity, we can distinguish between two things. There's time complexity, and there's space complexity. What is time complexity? Time complexity, we can also call the speed, right? Also, what we usually refer to as the performance, right? Now, performance does not exclusively refer to time complexity. It can also refer to space complexity, but most of the time when people talk about performance, like the performance of a computer or performance of a machine, performance of a program, of a video game, whatever, people are usually talking about the time, like, oh, this game is running at 20 frames per second, it has bad performance because it's too slow. Yeah, like the frames are too low because the computer cannot process the data fast enough. It's too slow, right? So the speed is low. Is basically like bad performance. But bad performance can also have to do with the space complexity. What is the space complexity? It is basically how much data your algorithm needs. Not how much data your algorithm works through, but how much data your algorithm creates, how much extra data, right? So we can think in practical terms, we can think how much memory we are allocating, right? So memory allocation. So usually if a algorithm allocates twice as much memory as another algorithm, we would say that this algorithm has twice the spatial complexity. So you have algorithm A, it allocates 2 megabytes of memory, and algorithm B, to perform the same operation, to give exactly the same result with the same input. So the input is the same, the output is the same. This has to be clear, right? Like, of course, if you have different input and different output, then you might need different allocations. But with the same input for the same output, let's say that this would allocate twice as much memory. We would say that the spatial complexity is 2 times the spatial complexity of A. Same thing for the speed, right? For the time complexity, if you have algorithm A that performs a certain operation in 10 milliseconds and B performs the same operations with the same input, same output in 20 milliseconds, then we would say that this has 2 times the complexity. So it's more complex, right? And complexity is bad. So usually we would say that this is a bad thing. We want to lower the complexity. And in this case, complexity is used in a little bit of an unusual way, right? Like it's not like that it's not that the algorithm is necessarily more complex, like harder to understand or harder to write or something. It's more that it's just like slower. So it could actually be a simpler algorithm that is slower. But nonetheless, we call this complexity. Now, we have some tools to analyze this complexity. The most known and the ubiquitous tool is a kind of notation, which we call the big O notation. What is big O notation? Very simple. It's a function that denotes how the complexity increases with the amount of data, with the input. So let's say that we have our max function here, right? We have some input, which is an array that has a certain amount of data, right? So we will put that data here in the x-axis. So this will be our array dot length. And in the y-axis, if I can draw it, we will put how many operations we will need to do, like how many of these operations we will need to do. This is pretty much the only operation we're doing. I mean, we're also doing this comparison here and stuff like that, and this addition, blah, blah, blah. But let's just focus on this one. Like, how many of these do we need to do? Yeah. We need to do, in this case, we need to do as many of these as there are values in the array. So if our array has 20 elements, we will do this 20 times. If our array has 100 elements, we will do this 100 times. So we call this a linear progression. So here we put the operations or the complexity in general, right? Like, so here we can say this is the complexity. And for now, let's just say like ops, right? Operations. In this case, it would be a linear complexity, something like that, right? So if you have 10 here, you have 10 there, right? More or less, yeah. Like, it's not exactly accurate, but you get the idea, right? And so on, right? But this curve could, in some cases, not look like this. Let's imagine an algorithm where I would do this. Let's say that I would have this array like that, and now I would call this n or something, right? So now I have two loops, and they both go for this whole length, right? So basically, if I have 10 elements in the array, we do, for the first element in this loop, for the first iteration in this loop, we do this 10 times. For the second element in this loop, we do this another 10 times, right? So actually, we're going to do 10 times 10. We're going to do 10 squared. So now for 10 elements, we're going to do 100, right? So we're actually going to do this here. And if we have 20, we're going to do 20 squared. So we're going to go way up there, right? Like, I will decrease here. I will change the scale here a little bit. So I will get rid of these 10s. Let's say that our 10 was here, right? And then our 100 would be there. This would be 100. So we would have point there. And then for the 20, right? For the 20, we would have 400. So 400 would be, I don't know, something like this. And then for, let's say for like 100 here, we would then go way up, right? Up to 10,000, right? 10,000. So our curve starts to look like that, right? Starts to look a little bit, well, it will look something like this, right? So it's exponential, right? So we have a situation. We have a situation where our algorithm can easily increase in complexity. So we have a few different patterns that are common. There's the linear. So this is, we would say that big O of n, and O here, that's where the big O notation comes from. The big O refers to the complexity. So the complexity of n equals n, right? So we could say the x equals the y. This is linear. Then we have some others like this one. So or maybe like that, where we would say O of n equals n squared, right? And then you could have some even worse ones like n cubed or something, right? Or n to the power of 4 or something like that, or to the power of 10, whatever it is. But then there are also some good ones. There's also a logarithmic scaling ones. So logarithmic is basically the opposite of an exponential. It starts to go up, it starts very high, but then levels off like that. Right? So this would be n equals log of n and stuff like that. And then there's also all kinds of things like log of n and blah 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 blah. Yeah, but you get the idea. Now I want you to pay attention to a couple things here. First of all is that we have this area here, right? You can see that, for instance, here the logarithm, it is actually in this whole area, like this whole area, it is actually higher. It has a higher complexity than the others. Okay. I also wanted to note that here, this is the n squared. It actually has a lower complexity than the others, right? And maybe even for a while, the n cubed is not looking so bad, right? Another thing I want you to notice is that the scale of this graph does not matter at all. It doesn't matter if here we have a 10 or a 10 million. That's 10 million. It doesn't matter at all. What matters is the curve and how the curve develops and how the curve changes. So do not focus on the specific numbers that would be on this graph. That's not what matters. What matters is how does the complexity scale as the data input scales. Okay? That's also why in the big O notation, we never use constants. So doing something like this doesn't make any sense. N plus 1, this 1 is irrelevant because the big O notation is not about the exact number of operations you do. it is about how does it scale. So if your n is 2, oh, if your n is 2, then this is relevant, right? This is relevant in this case because it will be 3, right? And then if your thing is 10, then this will be 11. So here there's a big increase. This one is very relevant. Here it's less relevant. And it's even less relevant when you have, 1 million or something. Then you will have, do I have the, yeah. Then you will have 1,000,001, and this is a tiny percentage of the total. And as it increases, this one here will become an even lesser and lesser and lesser percentage of the total complexity. So it becomes less relevant as the amount of data increases. So in big O notation, we completely ignore any of these constants. What is this constant? For instance, in our code, it could be like this. This is a constant. This is an operation that will always happen no matter how many elements are in this array. Also this, right? Like these two things, they always happen. Even if the array is empty, right? If I pass a null here, if I would pass a null or something like that, or an empty array, this and this would still happen. So basically, if my n is 0, the O of n, like in this case, it would be 1, right? There would still be one operation. But again, this is not important. This is not what big O notation is about. It's only about the growth, right? So we could write this down. So not the number of, or not let's not say number of operations, not the speed, right? Not the seconds or milliseconds, or however we want to measure the speed, not the seconds. It's not the bytes or megabytes or whatever. It's about scaling. This also means that when you look at your algorithm and you implement a certain algorithm that maybe you already know because you read somewhere online or whatever, that your algorithm has a bad complexity, let's say, like, oh, you implement an algorithm that has this kind of curve, right? Like it's like a n cubed, let's say. And then you look at, oh, there is an alternative that is actually like n squared, right? So n squared would be a little bit less crazy. But then you could say, well, it doesn't matter because the amount of data that I have is always going to be very small. Like I only have like three elements in my array, or my database only has 100 entries or something. Like I'm just sorting here like the top leaderboard of like the top 10 players or whatever. Like, it doesn't matter. Like it doesn't really matter if it's cubed or squared. Like you only have 2, right? And you could say, well, that's the difference between, like, if you're sorting 10 elements, right? If n equals 10, then that would be the difference between doing that many operations or doing that many operations. Depending on the operation, this might be completely irrelevant. Yeah, like maybe you're just comparing them to sort them, right? You want to sort the entries and you're just comparing them to each other, right? So you're doing like a bigger than or a smaller than or something. This is like nothing. Like your computer can do 1,000 of these like faster than your neurons can, perform, like do a synapse or whatever. Yeah, like this doesn't matter, it's irrelevant. Now if your n was 1 million, now this matters a lot more, right? Because now it's the difference, like it's the difference between, I don't know, 1 trillion and 1 quadrillion or whatever. Yeah, like that is much more significant. So it's all about the amount of data and also of the operations, right? Like some operations could take a long time. Like if you're just comparing, if you're just doing this or that or whatever, then it's very fast. But if your operation or what your algorithm is actually doing is like storing this value in a server, right? Like, so if you take your value here, so you take your file and you send it to the internet, right? And you have some ping, like you have 50 milliseconds of delay. Doing this 10 times per second or doing this 100 times per second makes a huge difference, right? Because here the operation, like the O of n, right? If this is 10, this means that you will do, if you have an n squared, this means you will do this 100 times, and this is 100 times 50 milliseconds, right? Or 100 network operations, which could also mean not just like the time, but also the bandwidth, the traffic, blah, blah, blah. Like your server might get, might also do some kind of processing. So you're also putting stress on the server and so on, right? If you have a n cubed, then you will do this 1,000 times. And that now starts to look much worse, right? This, because basically you're adding you're increasing the multiplier. So these things are relevant, but often they are not as relevant as people on the internet make it seem, right? Like you go on Stack Overflow or something like that, and people say, oh no, this algorithm is really bad because it's n squared or whatever. And it's like, yeah, but my list has literally 5 things and it will never have more than 5 things, and all I'm doing is like comparing them to each other, or like printing them, or I don't know, changing the color on a UI element or something like that, and it really doesn't matter that it's n squared. It could also be 10 n to the power of 10 or whatever. Like it would still be okay. Yeah, it can always be more efficient, but in some cases, it's just not worth the hassle to optimize. Okay, so this is the basis of algorithms and data structures. If you have any questions, please feel free to write them down and ask me in the next lecture or next opportunity, or send me a message on Discord or anywhere, or a comment, leave a comment here on YouTube, something like that. Okay, thank you.